Captions in English, please. So this is the third video of chapter 10, and we will go over units of energy and then specific heat capacity. So heat energy is measured in calories or joules. The joules are the units of the System International. So the calorie, by definition, and this has been established on purpose like that, the calorie is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. So if you use the prefix kilo in front, then a kilocalorie is the energy to raise 1,000 grams of water by 1 degree. And so you may think, oh, I know about calories. That's the unit we see on the nutrition facts for food. But be careful, there are two types of calorie units. There is the lowercase c calorie and the capital C calorie. And these are two different units. The one food capital C calorie, so the food calories are also called the nutritional calories. That's with the capital C, and they are equal to 1,000 smaller c calories, or 1 kilocalorie. So be careful. 1 capital C calorie is 1 kilocalorie for the lowercase c. So here are some energy conversion factors. 1 lowercase c calorie is 4.184 joules. And so the symbol for the joules is capital J. 1 capital C calorie is 1,000 calories. And then another unit here, the kilowatt hour. 1 kilowatt hour is 3.60 times 10 to the 6 joules. So the kilowatt hour are more used when we talk about electricity, electrical companies would talk about kilowatt hour when they talk about energy. So to give you an idea of the energy use in terms of these different units. So the energy required to raise the temperature of 1 gram of water by 1 degree, we said is 1 calorie with the lowercase c. And so because 1 calorie is 4.184 joules, then that's the amount you need for that. And then in capital C calorie, it's 0.001. In kilowatt hour, it's 1.110 to the negative 6. So it's a very small value with a lot of zeros in front. The kilowatt hour, are very large units. So the energy required to light a bulb, a 100-watt bulb for 1 hour, in joules, it's 3.6 10 to the 5. In calories, 8.6 10 to the 4. In calories, capital C calorie, or nutritional calorie, it's 86. And then in kilowatt hours, 0.10. And the energy used by average US citizen in one day, 9 10 to the 18 joules, 2.15 10 to the 18 calories. And in food calorie, it's 215,000 calories. And then in kilowatt hour, 250. So it looks like we are using a lot of energy. And so to give you an idea, for example, a bag of jelly beans, if you have a serving of it, 45 grams, you get 698 kilojoules. So, and per 100 grams, it would be 1,540 kilojoules. So it's kilojoules here. So that's a lot of energy just in 45 grams of jelly beans. So let's go through some examples about energy changes. So a candy bar contains 225 nutritional calories. And how many joules does it contain? So we need to do a conversion here, right? The given amount is 225 calories, nutritional calories. We want to find what it is in joules. So we will need to correct needed conversion factors. So ideally between calories and joules. But as we saw in the previous slides, there is no relationship directly between joules and nutritional calories. We know one nutritional calorie is 1,000 smaller calories, and one small C calorie is 4.184 joules. So we will need to do two conversions. First from nutritional calories to small C calories, and then from small C calories to joules. So because we are starting with nutritional calories, the first conversion factor will need to have the nutritional calorie in the denominator so that we can cancel the given unit here of calorie with the capital C. So then the first conversion factor will be 1,000 calories over 1 kilocalorie, one capital C calorie. Next, the second conversion factor needs to cancel the lowercase c calories. So the 1 calorie will be on the bottom and then the 4.184 joules on top. So when we write these together, so always start your calculations with the given amount. And here it's 225 capital C calories times 1,000 calories over 1 capital C calorie times 4.184 joules over 1 calorie. And we can see that the units of calories, nutritional calories cancel, the units of small calories cancel, and we are left with joule, which is what we want. In the calculator, you do 225 times 1,000 times 4.184, and that's 941,400 joules. So that's the calculator answer. We need to think about significant figures. And so the given amount has three significant figures. The 1,000 calorie over 1 capital C calorie are exact. These are by definition, so they will not limit the number of sig figs. The 4.184 has 4 sig figs because that's a measurement, given exactly 1 calorie. We have measured this in joules, and that's a measurement with 4 significant figures. So we need to keep 3 significant figures, the least number of significant figures here. So we keep the 9, the 4, and the 1. What comes after the 1 is a 4, so we keep the 1 a 1. And so that will be rounded as 941,000, or in scientific notation, 9.41 times 10 to the 5 joules. That's how we show 3 sig figs. So let's make the difference between heat and temperature of matter, right? These are two different concepts. The amount of temperature that an object increases depends on the amount of thermal energy added. So the thermal energy here is represented with the Q, that's the energy, and temperature is represented with T. And so delta T here represents the increase in temperature, so the change in temperature. And the symbol after that means proportional. It's proportional to Q, the thermal energy that is provided. So the more thermal energy provided, the higher the temperature will move up. And so if you double the added thermal energy, for example, the temperature will increase twice as much. This is what it means when it's proportional. They vary in the same proportion. The amount of temperature an object increases also depends on its mass. So mass is proportional to the thermal energy provided. So if you double the mass of your substance, it will take twice as much thermal energy to raise the temperature the same amount of degree. So Specific heat capacity. So substances can change temperature when thermal energy is added, but how much they change not only depends on the quantity of matter, so the mass, but also on the identity of the substance. So depending on what matter you have, it will not increase as fast with the same amount of energy. And so to define that, we have what we call the specific heat capacity, because this is the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So, we have tables that give the specific heat capacity of substances. And so they are given in calories per gram and per degree, or joules per gram and per degree, because it's the heat required to raise the temperature of 1 gram, so per gram, and to change the temperature by 1 degree, so per degree. So examples we have here: gold, 0.129 joules per gram and per degree. Aluminum, 0.895 joules per gram and per degree. So here the higher number for aluminum means you need more energy to raise 1 gram of aluminum by 1 degree than for gold. So the gold, is a more better conductor of heat. Liquid water needs 4.184 joules per gram and per degree. This is a very high value compared to, any other substances. And it's less for ice, 2.03 joules per gram and per degree, and steam also 2.02 joules per gram and per degree. So really, liquid water is the one that has the highest specific heat capacity. And so the larger a material's specific heat capacity is, and the more energy it takes to raise its temperature a certain amount. So it also means that it will have more thermal energy to transfer to other objects as it cools, right? All that energy is stored in the object until it cools. It can transfer then more energy. And so water's high specific heat is the reason it is such a good cooling agent. So it's used to cool, like, for example, nuclear central, or cool down with water, or any kind of industry that needs to cool down their machines uses water typically, from rivers. Unfortunately, they warm the water there. Well, they let it cool before they release it back to the rivers. But, water is used as a cooling agent because it absorbs a lot of heat for a relatively small mass. So how can water's high specific heat capacity be used to explain the temperature of an inland city like Sacramento versus a coastal city like San Francisco? You know that there is a difference between the climate in San Francisco versus Sacramento. Sacramento is more like a continental weather than San Francisco, which is more temperated. And so the reason is that, water's high specific capacity means that it will require much more time and energy to cool down or warm up. So the lakes and seas are much slower to respond to cooling and heating than the surrounding land masses. So, for example, rocks and the ground will absorb the heat more easily than a lake. And the ground will lose its heat more easily than the lake. So that's why the weather is much more temperated when you have a lot of water around it than in a landscape where there is mainly just ground and rocks and dirt. So that's a table of specific heat capacities. And so you see water at the bottom there, the solid and ice and then gas. And then all of the rest are mainly metals: silver, lead, iron, gold, copper, calcium, and aluminum. And you can see they all have values smaller than 1, right? Every one of them is lower than 1. Aluminum having the highest value here. And then carbon so carbon is a non-metal, but even a non-metal like carbon has a value lower than 1 for its specific heat capacity. Diamond 0.5 and graphite 0.7. So this really shows how water is really a special case. You need a lot of energy to warm it up and then cool it down. So heat gain or heat lost by an object. So the amount of thermal energy gained or lost by an object depends on 3 factors. So how much material there is, so that's the mass, what the material is, and so the specific heat capacity will help with that, and how much the temperature changed. So all of that will mean a different amount of energy. So the amount of heat exchanged between an object and its surrounding will depend on the mass of the object, the specific heat capacity of the substance the object is made of, and the temperature change that the object was subjected to. And so there is a formula for that. It's Q, that represents the amount of heat, equals ms delta T. So Q is the thermal energy or heat required in joules. M represents the mass of your substance in grams. S is the specific heat capacity in joules per gram and per degree. And then delta T represents the change in temperature, and that's going to be in degrees Celsius. So you see that all units will cancel out properly when you use those units for each of them. So let's use this formula and go through an example here. A 4.5 gram block of aluminum at room temperature, so 25.2 degrees Celsius, is placed into the freezer at negative 1.5 degrees Celsius. How much heat in calories did the block lose? And so it's the lowercase c here. The specific heat capacity of aluminum is 0.895 joules per gram and per degree. So what is given? There's a lot given here. And let's summarize this. Given the mass of the block of aluminum, 4.5 grams, the specific heat of aluminum, 0.895 joules per gram and per degree, and then the temperature change. So it goes from 25.2 degrees Celsius to negative 1.5 degrees Celsius. What is the question asking for? It's asking for how much heat did the block lose and in calories. So heat lost in calories. So we will need the heat equation, Q equals ms delta T. And here we have to calculate Q, because the heat in calories here is for Q. So we have the mass in grams, the specific heat in joules per gram and per degree, and then the temperature change in degrees Celsius. So we can plug in the values and we'll get Q. So it's 4.5 grams, the mass, times the specific heat capacity in joules per gram and per degree Celsius, times the temperature difference, which is, so when you do the temperature difference, you do the final temperature minus the initial temperature. So final temperature is negative 1.5 minus 25.2. So notice how here we have a subtraction to do before we do the multiplications. And so, and notice how the units cancel, the units of grams and of degrees cancel, and we're left with joules. So the heat will be calculated in joules. So the intermediate answer for the subtraction is 26.7 degrees Celsius. Actually, it's missing a negative sign there. So it's negative 26.7 degrees Celsius. Then you can do and so notice how when you are doing a subtraction, you pay attention to the least number of decimal places. And here both measurements had one decimal place. So we can keep then the one decimal place here, the 0.7, right? Next, you do the multiplication, and 4.5 times 0.895 times negative 26.7 gives a negative value for the heat, which is expected because it's heat that was lost by the system here. The system is the block of aluminum. It's been put in the freezer, so it has lost heat. And so that's why it's a negative value. So that's the calculator answer there in joules. And so we need to think about significant figures. However, the question was in calories. So you don't want to round the heat in joules because it's an intermediate answer. You will need to round only when you have the calories. But you can underline where you would stop. And so it depends on the number of significant figures. And here we have 2 sig figs in 4.5, 3 sig figs in 0.895, and 3 sig figs now in the temperature change. So the least number would be 2, and that's why the 0 is underlined, because you would keep 1 and then the 0 for 2 sig figs. However, you do not round, you keep everything that the calculator gives you to do the change now from joules to calories. And so to change from joule to calories, we need the equality between calories and joule, and it's 1 calorie equals 4.184 joules. So because we start with the given amount in joules, so we will want the 4.184 joules on the bottom of the conversion factor. So it's going to look like this, the value in joules times 1 calorie on top and the joules on the bottom. This way the joules cancel, and we will be left with calories, which is the unit we wanted. So in the calculator, you do negative 107.53425 and more digits if your calculator had some, divided by 4.184, and that's negative 25.7013 calories. So now we are ready to round, and here we have 2 sig figs from the heat, that came from the mass. We have 4 sig figs in the joules because that's a measured value, and the 1 calorie is exact. So still we need to keep 2 sig figs in the end, and so we keep the 2, we keep the 5. What comes after the 5 is a 7. So you need to round the 5 up to a 6. And that's going to be negative 26 calories. So that it's 2 sig figs. So that's the amount of heat that the block of aluminum lost.